From planets and stars to galaxies and vast cosmic webs, every new observation keeps pushing the limits of how big we think the universe is. Distances stretch beyond normal imagination. Light takes billions of years just to cross between clusters, and even the edge of what we can see is not the edge of everything that exists. Today we explore what scientists really mean by the size of the universe, from our local cosmic neighborhood to the farthest horizons of space-time. If you enjoy drifting through questions like this, please subscribe and share, and tell us in the comments what part of the universe's scale blows your mind the most. Thank you for watching. Now let's begin. Earth stands as a single inhabited world in a vast space, yet for most of human history it feels like the entire stage. Continents, oceans, mountains, and cities occupy only a thin shell on the surface of a sphere with a diameter of about 12,700 kilometers. Almost all human activity takes place within a layer only a few kilometers above sea level, under an atmosphere that becomes thin and cold within the first few tens of kilometers. Compared with the size of the planet, this living film is slight. A journey on foot across a valley, a voyage by ship across a sea, even a flight between distant continents, all remain confined to a narrow band wrapped around a single globe. The curvature of Earth is gentle and slow to reveal itself. To most observers at ground level, the surface feels flat, the sky appears like a dome, and the far horizon seems to mark the edge of everything that matters. Only careful watching of shadows, the changing height of the sun in the sky, and the motion of stars over many nights gradually show that this world is round and in motion. Earth rotates once every day, carrying landscapes, clouds, and oceans through a cycle of light and darkness. That rotation gives rise to familiar patterns of sunrise and sunset, and to steady winds and currents that blur borders between regions. At the same time, Earth orbits a star, tracing a broad path that defines the length of a year and the rhythm of seasons, though the details of this motion remain hidden from direct sense. The planet's crust, broken into plates that move slowly over millions of years, builds ranges of mountains and deep ocean trenches, but the scale of these changes is so large in time that human lifetimes only see a moment of the process. The solid surface rests on a deeper mantle of hot rock and surrounds a core of metal. Yet these inner layers are distant from everyday experience, inferred from seismic waves and gravity rather than direct sight. Even within this one world, there are many layers of scale: a grain of sand beside a mountain, a river beside an ocean basin, a small island compared with a continent. A single city holds millions of lives, but from high above that city would shrink to a patch of light, and then to nothing at all as attention shifts to the form of the whole planet. Earth's total mass holds an atmosphere in place and shapes the paths of orbiting satellites. But to an individual observer, its gravity is simply the pull that keeps feet on the ground. Spacecraft and space stations that circle the planet travel only a few hundred kilometers above the surface, safely inside the thin bubble of air and the reach of Earth's magnetic field. From that height, coastlines and weather systems come into view, yet the planet still fills the frame, and the sense of being close to one world remains. The difference between human scale and planetary scale already introduces a sense of hidden magnitude. A person can walk perhaps a few tens of kilometers in a day, cross a continent in many days or weeks, and circle the globe in a modern aircraft in less than a week. Yet the full size of the planet remains difficult to feel directly. Maps and globes compress continents and oceans into small diagrams, allowing the mind to see at once what the body cannot ever traverse in a single glance. Measurements of meridians and shadows show that the circumference of Earth is about 40,000 kilometers, but the numbers remain abstract without a wide comparison. On this globe, deserts stretch for thousands of kilometers, oceans cover most of the surface, and polar regions hold ice sheets whose thickness reaches several kilometers, Yet all of these features cling to one small sphere suspended in space. Across time, the contrast between human life and planetary history adds another layer of scale. An individual life spans at most many tens of years, while the planet itself forms over about 4.5 billion years and carries fossils that record hundreds of millions of years of changing climates and species. Civilizations rise and fall over thousands of years, yet the continents that support them drift only a small distance in that interval. Every recorded event in human history, every birth and death, every structure that has ever been built, currently resides, or once resided, within this shallow layer on the Earth's surface. The planet carries a biosphere of forests, grasslands, reefs, and polar seas that thrives under a narrow range of temperatures and pressures, made possible by a stable orbit and a protective atmosphere. Simple chemical elements organize into living cells, and over long spans of time, evolution fills continents and seas with many forms of life. Among them, a species capable of abstract thought begins to measure, to record, and to imagine regions beyond direct reach. As tools improve, this species sends instruments to mountain summits, to the deep ocean, and eventually to the upper atmosphere and beyond. Photographs from the edges of near space show Earth as a curved limb against blackness, and then as a nearly full disk, with weather systems swirling above familiar coastlines. Later views from farther away, taken by spacecraft leaving near-Earth orbit, present the planet as a small sphere set against a dark background, with the Moon sometimes nearby as a smaller companion. These images replace old ideas of a flat world with a clear view of a planet that is finite bounded and small compared with the dark around it. Yet against the scale of a human life it still appears immense. A person may cross only a tiny fraction of the surface in one lifetime, while the planet persists through many generations. The contrast between the modest reach of individual travel and the global distances of the world lays the foundation for the larger journey outward. Earth becomes the reference point, the starting frame of size, from which larger structures will be measured. To ask how big the universe really is, the narrative first settles on the dimensions of this single world and the thin layer in which life arises. Once that starting scale is steady in mind, it becomes possible to move outward, step by step, beyond clouds, and weather beyond the pull of Earth's gravity, and into distances where a whole planet will soon shrink to less than a point. From the vantage point of a planet already recognized as a sphere in space, the next clear step outward is the small companion that circles it. The Moon orbits Earth at an average distance of about 384,000 kilometers. This number is large compared with the size of Earth, yet small compared with the distances that follow. In the sky, the Moon appears roughly the same angular size as the Sun because of a coincidence between its distance and diameter, but the underlying scale is set by orbital mechanics and gravity. The Moon completes one circuit around Earth in a little more than 27 days, keeping essentially the same face turned toward the planet because its rotation period matches its orbital period. Over that time, the angle between the Sun, Earth and Moon changes, and the sequence of lunar phases follows from that simple geometry. The Moon reflects sunlight rather than producing its own light, so every change in brightness comes from a change in illumination, not from a change in the Moon itself. The gap of hundreds of thousands of kilometers between Earth and the Moon is wide enough that travel across it remains an exceptional technical achievement. Spacecraft that carry humans to lunar orbit and back take several days to cross this distance, moving far faster than any vehicle that operates within the atmosphere. Robotic landers and orbiters follow similar paths, adjusting their trajectories with careful burns so that they arrive at the right point in the Moon's orbit. Even with such speeds, the time needed to travel shows that the Earth-Moon system already occupies a scale far beyond everyday journeys. Light covers the same distance in about 1 1/3 seconds. radio signals sent from Earth to a spacecraft near the Moon, and then returned take a little over 2 seconds for the full trip. This delay is small compared with the timescales of daily life, but large enough that commands and responses cannot be truly instantaneous. Laser beams directed at retroreflectors on the lunar surface return with a measurable delay, allowing the distance to be tracked to within a few centimeters. Measurements of this kind show that the Moon slowly moves away from Earth by a small amount each year as tidal interactions redistribute rotational energy. The orbit is not a perfect circle. At some times the Moon is slightly closer, at some times slightly farther away. The nearest point, called perigee, lies tens of thousands of kilometers closer than the farthest point, called apogee. As a result, the apparent size of the Moon in the sky changes subtly over the course of a month. During total solar eclipses, when the Moon passes directly in front of the Sun, the match between apparent sizes becomes exact only when the distance is in the right range. At slightly greater distances, the Moon no longer fully covers the Sun and a bright ring remains. These events provide clear direct demonstrations that the distances involved are real geometric separations in space rather than abstract numbers. The history of scientific work on the Earth-Moon distance traces a path from rough estimates to precise tracking. Early astronomers used geometry and parallax comparing the position of the Moon against background stars as seen from different points on Earth. By measuring tiny shifts in position, they infer its range in kilometers and relate it to the size of Earth. Later radar and laser ranging refine the values and anchor the lunar distance in a network of units defined by the speed of light. Each improvement in precision confirms that the empty space between Earth and its satellite is wide but finite a gap that can be crossed by machines built with the right design. From the surface, the Moon influences tides, stabilizes Earth's axial tilt, and contributes to the long-term climate, yet these effects depend on a balance between distance, mass, and motion. If the Moon is much closer, tides are more extreme, and the orbital period is shorter. If it is much farther away, its role in stabilizing the tilt weakens. The present distance represents one stage in a slow evolution. In the far past, the Moon orbits much nearer to Earth, and in the far future, it will orbit farther away. The current state is only one frame in a long sequence that spans billions of years. This knowledge adds a temporal dimension to the idea of scale. The distance is not only a measure of space, but also a marker of age accumulated over deep time as energy flows through the Earth-Moon system. The lunar surface itself reinforces these scales. Its lower gravity, about 1/6 that of Earth, means that trajectories of dust and rock follow higher arcs, and impact craters keep their shape for long periods. From orbit, mountains, basins, and ancient lava plains are visible across large fractions of the globe at once. The absence of air and weather preserves features for hundreds of millions of years, turning the surface into a record of events that reach back to the early history of the solar system. Every crater and basin marks a past encounter with objects that move through space on paths measured in millions of kilometers. From above, the Earth-Moon pair appears as a double system, a large planet and a smaller companion circling a shared center of mass that lies beneath Earth's surface but shifted slightly away from the exact center. Together they orbit the Sun, but at this step of the journey, the focus remains on the radius of the lunar orbit as the first clear rung of cosmic distance. Compared with the size of Earth, this separation turns the planet and Moon into small beads on a wire of empty space. Compared with the Earth-Sun gap that follows it is still a modest step. The mind begins to adjust by holding all three scales at once: the human body, the planetary sphere, and the orbit of the Moon. The contrast between them prepares the way to extend the same method outward to the next layer, where the primary star of the system waits at a distance hundreds of times greater than the space between Earth and its satellite. Beyond the Earth-Moon pair, the main source of light and gravity for the entire system comes into focus. The Sun is an ordinary star by galactic standards, yet for the planets bound to it, its presence defines almost everything. Earth orbits this star at a distance called 1 astronomical unit, set at about 150 million kilometers. This separation is more than 300 times the average distance between Earth and the Moon. The difference in scale moves the story from a nearby companion to the true centre of the solar system. Light leaving the surface of the Sun takes about 8 minutes and 20 seconds to cross the gap to Earth. In that time, Earth has rotated a small fraction of a turn and has moved forward along its orbit by many thousands of kilometres. The same journey by a spacecraft would take months at present speeds. At velocities similar to those of a modern airliner, the trip would extend to many years. Even within this inner region, the distances are large enough that human senses need numbers, models and images to hold them. The Sun itself is a sphere with a diameter of about 1,400,000 kilometres, more than 100 times the diameter of Earth. It consists mainly of hydrogen and helium under conditions of high temperature and pressure. In its core, nuclear fusion converts hydrogen into helium, releasing energy that takes a long time to filter outward through the dense inner layers. Once that energy reaches the visible surface, it streams into space as light and other forms of radiation in all directions. A very small fraction of this output intersects Earth and the other planets. Despite being only a tiny share of the total, it is enough to set the surface temperature of Earth drive, weather-feed photosynthesis, and maintain the conditions in which liquid water can persist over geological spans of time. In the inner solar system, 4 rocky planets circle the Sun along orbits that lie roughly in a single plane. Mercury, closest to the star, completes a revolution in only about 88 Earth days. Venus follows with an orbital period of about 225 days. Earth takes about 365 days, and Mars orbits more slowly in about 687 days. These time spans connect directly to the distances involved. Closer planets feel a stronger gravitational pull and move faster along tighter paths. More distant ones move more slowly along wider tracks. The layout of these orbits creates a simple architecture, a star at the centre surrounded by concentric paths of worlds that never collide because each one occupies its own lane. Yet the space between them remains mostly empty. At the scale of planetary diameters, the orbits are separated by tens of millions of kilometres. The Earth-Sun distance becomes a natural unit for describing this structure. Mars orbits at about 1.5 astronomical units from the Sun. This means that at some points in their respective paths, Earth and Mars are relatively close, with a separation of around tens of millions of kilometres, and at other times they are on opposite sides of the Sun, separated by hundreds of millions of kilometres. Spacecraft launched from Earth time their departures to take advantage of the periods when the distance is smallest. Even so, travel to Mars with current propulsion takes many months, and the window for efficient transfer repeats only after certain alignments of the planets recur. Within this inner region, heat and light from the Sun decrease with distance. Mercury receives several times the solar energy that Earth does, leading to extreme surface temperatures. Venus, with its dense atmosphere rich in greenhouse gases, traps heat so effectively that its surface remains hotter than that of Mercury, despite orbiting farther from the Sun. Earth maintains a balance where oceans can exist in liquid form, and Mars, colder and more tenuous in air, preserves ice at its poles and traces of past liquid water in valleys and basins. The idea of a habitable zone, a band around a star where liquid water can persist on a rocky surface, emerges from this pattern. The exact boundaries of such a zone depend on atmospheric composition and other factors, but the inner planets show how orbital distance and surface conditions interrelate. The scale of the Earth-Sun separation also provides a reference for measuring and mapping the orbits of smaller objects. Between Mars and Jupiter lies the main asteroid belt, a region populated by countless rocky bodies of many sizes. Each asteroid follows its own path around the Sun, yet together they occupy a broad ring whose inner edge sits several astronomical units from the star. In comparison with the belt, the orbits of the 4 inner planets form a compact system close to the radiating surface of the Sun. This contrast between inner and outer regions becomes clearer as the narrative moves outward, but even now the difference in scale is apparent. The distances from the Sun to Mercury, Venus, Earth, and Mars form a small set of values compared with the orbits of the giant planets that follow. Understanding the Earth-Sun distance also transforms the sense of time. When sunlight that now warms Earth left the solar surface, the planet was slightly closer to or farther from the star, depending on where it was in its elliptical orbit. By the time that light reaches the ground, events on Earth have already moved on. When the Sun is viewed as it appears at any moment in the sky, the image shows the star as it was about 8 minutes earlier. This delay is small compared with the age of the solar system, but it is a reminder that space and time are linked by the finite speed of light. In planetary terms, the system is already large enough that the present is always separated from direct observation by small but real intervals of time. Measurements of the Earth-Sun distance originally draw on the geometry of transits where Venus passes directly between Earth and the Sun, and on the dynamics of planetary motion described by the laws of gravitation. Later, radar ranging to nearby planets and spacecraft tracking refine the scale. Once one orbit is fixed in kilometers, others follow through the patterns encoded in orbital periods and gravitational parameters. The structure of the inner solar system becomes a precise framework rather than a rough sketch. Each planet pursues a path whose size and timing are known to high accuracy. The Sun's mass concentrated in a central region far smaller than the diameter of its orbiting system holds all of these motions in place through gravity alone. In this architecture, Earth and the other inner planets form a small inner family, gathered close to a star whose energy output defines the conditions of their surfaces. The distances between them, measured in tens or hundreds of millions of kilometers, already exceed everyday intuition. Yet compared with scales that lie ahead, the entire inner system is compact. If the orbits of Earth and Mars are taken as a local yardstick, the separation from the Sun to the outermost planets will stretch that yardstick many times. The gap between the Sun and the edge of the region where its light still dominates the sky of a planet will reach billions of kilometers. As the view moves outward to Jupiter, Saturn, Uranus, and Neptune, the familiar warmth of the inner solar system will give way to colder, more rarefied conditions, and the true reach of the Sun's gravitational domain will begin to emerge. Beyond the orbit of Mars, the structure of the solar system changes character. The warm region of rocky planets gives way to a colder zone where giant worlds made mostly of gas and ice circle the Sun at far greater distances. Between Mars and the first of these giants lies the main asteroid belt, a broad ring that begins several astronomical units from the Sun. Although pictures sometimes show this belt as a crowded swarm of rocks, almost touching measurements and spacecraft flights reveal that it is mostly empty space. Individual asteroids are separated by large gaps so that a spacecraft can pass through without weaving between obstacles. The total mass of all these bodies together is small compared with a single large planet, yet the belt marks a structural boundary. Inside it, orbits belong to small rocky worlds. Beyond it, the planets become much larger and less dense, with thick envelopes of hydrogen, helium, and other light substances. Jupiter is the first of these outer giants. It orbits the Sun at about 5 astronomical units, or 5 times the Earth-Sun distance. That is roughly 750 million kilometers from the Sun. Its diameter is about 11 times that of Earth, and its mass is more than 300 times greater. The planet is dominated by deep cloud layers, with bands, storms, and vortices that have persisted for long periods. The largest of these storms, known as the Great Red Spot, has been observed for centuries and spans a region larger than Earth itself. Around Jupiter, dozens of moons move along paths governed by the planet's strong gravity, forming a miniature system within the larger solar system. Some of these satellites, such as Europa and Ganymede, hold internal oceans beneath ice shells, and their orbits resonate with one another in a pattern set by gravity. Farther from the Sun, at about 10 astronomical units, lies Saturn. Slightly smaller and less massive than Jupiter, Saturn still dwarfs Earth in size. Its most striking feature is a complex system of rings made of ice and rock fragments that circle the planet in a thin, bright disk. The rings are broad in diameter, but very shallow in thickness, demonstrating another contrast between lateral extent and vertical scale. Like Jupiter, Saturn hosts many moons, including Titan, which has a dense atmosphere richer in nitrogen than Earth's, and lakes of liquid hydrocarbons at its surface. The orbits of these moons and the structure of the rings both reflect the subtle balance between gravity collisions and tidal forces at work over long periods. Beyond Saturn, the light from the Sun continues to diminish. Uranus orbits at about 19 astronomical units from the Sun. Its distance pushes it into a region where the Sun appears as a small bright star rather than a large disk. Uranus is an ice giant with a composition that includes more water, ammonia and methane relative to hydrogen and helium. Its atmosphere gives it a blue-green colour in reflected light. One unusual feature of Uranus is its extreme axial tilt. The planet's rotation axis is tipped so far that it almost lies in the plane of its orbit. As a result, each pole experiences long periods of continuous illumination, followed by long periods of darkness over the course of its long year. Several rings and a group of moons complete the system, all sharing the tilted orientation. Still farther out, at about 30 astronomical units from the Sun, circles Neptune. Slightly smaller than Uranus but similar in bulk composition, Neptune is another ice giant with high winds and a deep atmosphere containing methane that absorbs red light and gives the planet a rich blue appearance. The energy budget of Neptune includes not only absorbed sunlight, but also heat from its interior, which drives weather patterns even at this great distance from the Sun. Neptune also hosts a system of moons, the largest of which, Triton, follows a retrograde orbit that suggests it may once have been an independent object captured by Neptune's gravity. The distances that separate these outer giants highlight how the scale of the solar system expands. The gap from Jupiter to Saturn is greater than the distance from the Sun to Mars. The jump from Saturn to Uranus adds another span of space in which no large planet orbits. From Uranus to Neptune there is yet another wide interval. These separations are measured in hundreds of millions or even billions of kilometers. A spacecraft traveling from one of these orbits to the next must cross regions where the Sun's gravity still dominates the overall motion, but where light and solar wind arrive weakened. Space probes sent to visit these planets, such as the Voyager and Pioneer missions, and more recent orbiters, take many years to reach their targets, even with planetary gravity assists. When they arrive, the round-trip time for radio signals becomes long. At the distance of Neptune, a radio message sent from Earth may take several hours to arrive, and the response takes the same time to return. Communication becomes an exchange with long pauses limited by the speed of light across a space that continues to widen as the planet and spacecraft move along their paths. At the orbits of Jupiter and Saturn, sunlight is reduced to a fraction of the intensity it has at Earth. Solar panels must be larger to gather the same power, and beyond a certain distance it becomes more practical to rely on radioisotope power sources that do not depend on direct light. This steady fading of sunlight with distance gives a physical sense of the growing size of the system. The Sun remains the central source of light, but its apparent brightness and angular size shrink steadily as the orbit radius increases. The outer planets therefore inhabit a realm of long orbits, low temperatures and slow changes. The time each giant planet takes to complete a single orbit around the Sun spans many Earth years. Jupiter needs about 12 years, Saturn about 29, Uranus about 84, and Neptune about 165. During a human lifetime, an observer on Earth sees Jupiter circle the Sun several times, Saturn once or twice, and Uranus perhaps once. Neptune completes only a fraction of an orbit across the course of an average life. Time and distance intertwine. The farther a planet lies from the Sun, the longer its year and the larger its path. The outer giants also mark the boundary of what is easily visible from Earth with modest instruments. Uranus is just within reach of the unaided eye under dark skies, though it appears as a dim point. Neptune requires telescopes to detect and track. Beyond their orbits lies a region where small icy bodies such as those in the Kuiper Belt and scattered disk follow distant inclined paths. Objects like Pluto Eris and many others occupy this outer debris field. Their discovery in the late 20th and early 21st centuries reveals that the solar system continues well beyond the orbit of Neptune, but in a form that is faint and dispersed. The presence of these bodies hints at an even more extended reservoir of comets and icy fragments farther out the region known as the Oort cloud. At this stage of the journey, the planetary system already stretches across spans that reach billions of kilometers from the Sun, yet the gravitational influence of the star extends still farther. The orbits of the 4 giant planets, their moons, their rings, and the belts of small bodies around them together outline a vast layered structure, but this structure remains only the inner portion of the Sun's full domain. To understand where that domain truly ends and interstellar space begins, the narrative must follow the paths of the spacecraft that have ventured beyond the orbits of the giant planets and into the region where the solar wind meets the sparse material between the stars. The path outward from the orbits of the giant planets follows the machines that humanity has already sent into that region. Among them, 2 spacecraft play a central role in tracing the true reach of the Sun's influence. Voyager 1 and Voyager 2 leave Earth in the late 1970s, launched by a national space agency to take advantage of a rare alignment of the outer planets. Gravity assists from Jupiter and Saturn bend and accelerate their paths, turning limited rocket power into long-term motion that carries them toward the edges of the solar system. After sweeping past the giant planets and sending back images and measurements of their clouds, rings, moons, and magnetic fields, the Voyagers continue outward on trajectories that no longer loop back. Their speeds are high by the standards of chemical rockets, roughly many tens of kilometers per second relative to the Sun. Yet even at such velocities, the time needed to reach the distant boundary of the heliosphere stretches over decades. As the spacecraft move away, the light from the Sun grows dimmer, and the apparent size of the star shrinks. Solar panels would no longer be effective so far from the source, so the Voyagers carry radioisotope power systems that convert heat from radioactive decay into electricity. This steady but limited power supports instruments' onboard computers and radio transmitters that send narrow streams of data back toward Earth. The signals weaken with distance and must be collected by large radio dishes on Earth, but careful engineering keeps contact alive even as the gap widens to tens of billions of kilometers. Around each spacecraft, the physical environment changes gradually. Near the Sun, a stream of charged particles known as the solar wind flows outward in all directions at hundreds of kilometers per second. This wind creates a large bubble in the thin gas between stars. The bubble, called the heliosphere, is filled mostly with particles and magnetic fields carried outward from the Sun. Beyond it lies the interstellar medium, a much more slowly moving mixture of gas dust and magnetic fields that belongs to the broader galaxy rather than to any single star. The boundary between these 2 regions is not sharp like a wall. Instead, there are layers. At a certain distance from the Sun, the solar wind slows abruptly from supersonic to subsonic speeds under the pressure of the external medium. This region is called the termination shock. Beyond it lies the heliosheath, where the slowed solar wind continues to push outward against the interstellar medium. Farther still lies the heliopause, the surface, where the outward pressure of the solar wind and the inward pressure of the interstellar medium come into balance. The exact shape of this boundary depends on how fast the Sun moves through the galaxy, and on variations in the surrounding medium. It may be somewhat comet-shaped, compressed on the side that faces the direction of the motion, and extended into a long tail behind. The voyagers, each on its own path, cross these regions at different points and times. Instrument readings show changes in particle densities, energies, and magnetic field directions that mark the transition from solar plasma to interstellar plasma. When Voyager 1 crosses the heliopause in the early 21st century, it becomes the first human-made object to enter interstellar space. This phrase does not mean that it has left the solar system entirely, since the Sun's gravity and the distant reservoir of icy bodies known as the Oort cloud still extend much farther out. Instead, it means that the spacecraft has left the region dominated by the solar wind and entered a region where the particles around it are part of the wider galaxy. At these distances, the sense of scale deepens. Radio commands sent from Earth travelling at the speed of light take many hours to reach a Voyager, and the responses take an equal time to return. Control therefore depends on careful planning rather than direct continuous adjustment. Measurements received today describe conditions that prevailed many hours earlier at the spacecraft. Even light from the Sun shining on the Voyagers from behind takes many hours to catch up with them. The spacecraft themselves carry no means to slow down significantly, so they will continue to move outward, indefinitely coasting along paths set by their final gravity assists and by the combined pull of the Sun and the galaxy. Decades before they reach the heliopause, the Voyagers provide another perspective on scale by looking back. In the early 1990s, after completing the main part of its planetary tour, Voyager 1 turns its cameras toward the inner system from a distance of roughly 6 billion kilometers. In the resulting image, Earth appears as a faint pale point suspended in a beam of scattered sunlight. The frame contains no visible detail of continents or clouds, only a single pixel of light that represents an entire world. All the complexity of oceans, weather, life and history fits within that single dot at this distance. The picture makes a simple factual statement about scale. A shift from a nearby orbit to a position many billions of kilometers away is enough to reduce a planet to something that barely registers on a sensor. At the same time, the probes record the spectrum and intensity of particles around them, building up a profile of how the solar wind evolves with distance. They detect energetic particles accelerated at the termination shock measure, the flow of lower energy particles in the heliosheath, and finally sense the increase in galactic cosmic rays beyond the heliopause. Changes in magnetic field direction reveal when the field dominated by the Sun gives way to the field carried by the interstellar medium. These observations help to estimate the size of the heliosphere, showing that its boundary lies at a distance of many tens of astronomical units from the Sun, far beyond the orbits of the giant planets. Yet when these distances are compared with the separation to the nearest star, they still occupy only a small inner zone. The heliosphere, though vast, is a local structure formed by one star, and its wind moving through the thin material between stars. Other stars carry their own winds and form their own bubbles, and these regions may sometimes touch or overlap. Between them lies the broader interstellar medium of the galaxy, threaded by magnetic fields and enriched by material from past generations of stars. The Voyagers therefore stand at a threshold. They have travelled far enough to leave the direct influence of the solar wind, but remain well inside the broader gravitational reach of the Sun, and far inside the distance to even the closest stellar neighbours. Their journey clarifies the idea that the solar system is not sharply bounded by the orbit of the outermost planet. Instead, it has a layered edge, defined first by the orbits of the giants, then by belts of small bodies, then by the extent of the solar wind. Beyond the heliopause, the environment belongs increasingly to the galaxy, rather than to the single star at its centre. This step in scale shifts the focus from a planetary system dominated by one object to a background medium that connects many such systems. From here, the next natural question concerns how far the Sun's gravity continues to hold small bodies in bound orbits, and how far the sparse population of icy objects extends into the dark. That question leads outward to the concept of the Oort cloud, a distant envelope whose full size remains uncertain, and whose outer edge begins to approach the halfway mark to the nearest stars. Beyond the heliopause, the environment through which the voyagers travel belongs increasingly to the wider galaxy, rather than to the solar wind, yet the Sun's gravity still reaches far beyond this boundary. The heliosphere marks where the charged particles from the Sun give way to the interstellar medium, but it does not mark the end of the solar system in a gravitational sense. Small icy bodies can still orbit the Sun at distances many times greater than those of the giant planets, tracing paths so wide that each revolution takes millions of years. This remote region, called the Oort cloud, is not a solid shell, but a vast sparse population of comet nuclei. It is thought to form a roughly spherical envelope around the solar system extending outward far beyond the orbits of Neptune and the Kuiper belt. No telescope has yet imaged the individual bodies that make up this cloud, because each nucleus is small, dark, and far from the Sun. Instead, the existence of the Oort cloud is inferred from the behaviour of long-period comets that appear in the inner solar system. These comets arrive on orbits that are highly elongated and oriented in almost every possible direction. Their paths suggest that they begin far from the Sun, fall inward under gravity, briefly grow bright as their ices vaporize near the star, and then return to the deep outer darkness, unless their orbits are altered by encounters with planets. The typical distances associated with the Oort cloud are expressed in astronomical units, the same unit defined by the Earth-Sun distance. The inner edge of the cloud may lie several thousand astronomical units from the Sun, where the influence of the giant planets begins to fade and the gravitational pull of the galaxy starts to matter. Beyond that inner region, the density of bodies may increase to a broad maximum, and then gradually decrease again toward an outer edge that might lie around 50,000 to 100,000 astronomical units from the Sun. At such distances, the time it takes an object to complete one orbit around the Sun can reach tens of millions of years. The Sun's gravitational grip on these bodies is gentle. Passing stars, giant molecular clouds, and the overall tidal field of the Milky Way can all disturb their orbits. Some perturbations send nuclei inward, turning them into long-period comets that occasionally visit the inner system. Others may eject them entirely, setting them on paths that leave the solar system and turn them into interstellar objects. To describe these scales in more familiar terms, astronomers use the light year, the distance that light travels in a vacuum in 1 year. 1 light year is about 10 trillion kilometres, a number so large that it is seldom written out in full. Expressed in light years, the outer reach of the Oort cloud may approach a distance of about 1 or 2 light years from the Sun. This means that the region of scattered icy bodies under the Sun's weak gravitational influence may extend almost halfway to the nearest known star. Within this interpretation, the Oort cloud defines a natural outer boundary for the solar system inside it. Small bodies can remain bound to the Sun over cosmic timescales. Beyond it, the gravitational pull of other stars and of the galaxy as a whole takes over. Even within the cloud, emptiness dominates. If the total number of comet nuclei is large, perhaps many trillions, they are spread across such a huge volume that the average separation between neighbours could be comparable to the distance between planets in the inner system. A spacecraft moving through the Oort cloud would almost certainly not encounter a comet nucleus unless it were guided with precise foreknowledge of specific orbits. The cloud is therefore not a solid barrier, but a statistical region defined more by the probability of finding such bodies than by any continuous material. The idea that the solar system includes this distant shell of debris changes how its size is perceived. The orbits of the familiar planets, even those of Uranus and Neptune, occupy only a tiny central region of the overall structure. If the solar system is drawn with the Oort cloud included, the planetary zone near the Sun becomes a small dense core at the centre of a large faint sphere. The heliosphere with its boundary at the heliopause sits well inside this larger gravitational system. The voyagers after crossing the heliopause are in interstellar space in terms of plasma conditions, but are still less than a tenth of the way to the putative outer edge of the Oort cloud. Their journeys give direct information about the boundary of the solar wind, but only indirect clues about the location and population of the distant icy reservoir. Evidence for the cloud continues to arise mainly from the statistics of long-period comets. By cataloguing the shapes and orientations of cometary orbits, researchers estimate how many source objects must exist in the distant reservoir and how they are distributed. Some models suggest an inner Oort cloud, sometimes called the Hills cloud, that lies closer to the Sun and feeds the outer region with new comets as older ones are lost. Others explore how the early passage of the Sun through a crowded birth cluster might have filled the outer reservoir with material perturbed from the protoplanetary disk. While details remain uncertain, the broad picture is consistent. The solar system is surrounded by a very extended halo of frozen bodies that occupy distances where the Sun is only one among many sources of gravity. This understanding introduces another important scale, the Hill sphere of the Sun, which marks the region within which the Sun's gravity dominates over that of the galaxy and binding orbiting companions. The outer parts of the Oort cloud may lie near the edge of this sphere. Beyond that edge, any small body that once belonged to the solar system becomes more securely attached to the galaxy as a whole than to the individual star. At this point in the outward journey, the narrative has moved from the dense inner system of planets and their moons through the fading solar wind and into a domain where the distinction between solar system and interstellar space blurs. The Oort cloud and the Sun's Hill sphere represent the last layers where the star's direct influence on orbiting debris is significant. Beyond them, the distances to the nearer stars become the next natural yardstick. When those distances are expressed in light years, it becomes clear that even a solar system enlarged to include the entire Oort cloud is a small structure embedded within a much larger stellar neighbourhood. With the outer boundaries of the solar system set by the distant Oort cloud, the next scale to consider is that of the stars nearest to the Sun. These neighbours are not arranged in a neat shell, but scattered through space at various distances and directions. The closest known stellar system, Alpha Centauri, lies in the southern sky and consists of at least 3 stars bound together by gravity. 2 of them are Sun-like stars that orbit a common centre, while a third, smaller red star called Proxima Centauri moves around the pair on a much wider path. The distance from the Sun to this system is a little more than 4 light years. In kilometres, this separation is on the order of tens of trillions, so large that the numbers themselves become difficult to hold in mind without a more compact unit. The light year provides that unit by tying distance directly to travel time at the speed of light. A beam of light leaving the Sun and heading toward Alpha Centauri would spend more than 4 years crossing the gap, travelling through a region where there are no large bodies to intercept it. At the speeds of current spacecraft, the times required become extreme. A probe moving as fast as Voyager 1 would take tens of thousands of years to reach the nearest star. Even if future technology increases cruise speeds by substantial factors, interstellar travel remains a project on timescales far longer than any journey undertaken so far. This gap emphasizes that each star with its own planets and debris occupies a domain separated from others by expanses of almost total emptiness, where the density of gas and dust is far lower than even the best vacuums produced in laboratories on Earth. Within a sphere of radius 10 light-years around the Sun lies a small community of stars. Many are faint red dwarfs with masses smaller than that of the Sun and with lower surface temperatures. A few are similar to the Sun in size and brightness. There may be brown dwarfs objects too small to sustain hydrogen fusion, yet more massive than planets. Observations in many wavelengths reveal that several of these nearby stars host planets. Some of those planets lie in zones where a rocky surface could, in principle, maintain liquid water given favourable atmospheric conditions. Others are large gas giants or close-orbiting worlds with conditions very different from those on Earth. Despite these discoveries, the details of surface environments, atmospheres and possible chemistry on most exoplanets remain unknown, because at these distances each planet is far too small and faint to resolve directly. Most are detected through subtle changes in the light of their host stars, or through tiny shifts in stellar motion induced by their gravity. The interstellar medium that fills the space between these stars is not completely empty, but the material is so diffuse that a human-made spacecraft would travel enormous distances without striking even a single grain of dust large enough to damage it. The medium contains mostly hydrogen and helium gas, along with traces of heavier elements and dust grains. It is threaded by magnetic fields and structured into regions of different temperatures and densities. The Sun currently resides in a region of relatively low density, often called the local bubble, likely carved out by past supernova explosions. Even within this bubble, however, the scale of distances dwarfs the sizes of the stars themselves. Each star is comparable in size to the Sun, perhaps 1 million kilometers in diameter, yet they are separated by distances measured in trillions of kilometers. The ratio between the diameter of a star and the distance to its nearest neighbors is enormous, making direct interactions rare outside of binary or multiple systems where stars form together. Gravitationally, however, the influence of each star extends indefinitely, fading with distance, but never dropping exactly to zero. The balance between the pull of one star and that of the rest of the galaxy sets the scale of each stellar hill sphere, defining the region where long-term bound orbits can exist. For the Sun, this region includes the Oort cloud. For other stars, equivalent shells surround their own systems. Where these outer regions come close, the weak gravity from passing stars or from overall galactic tides can alter orbits and trade material between systems over millions of years. From the perspective of human technology, the interstellar distances are so great that communication itself takes on a new character. Radio waves broadcast from Earth spread outward at the speed of light in all directions, forming a growing sphere of influence. At present, these signals have had time to travel only a little less than 100 light-years since the earlier strong transmissions began. Within that sphere lie thousands of stars, including some of the nearest neighbors. Outside it, the radio noise from Earth has not yet arrived. Even within this bubble, the signals weaken as they spread, and natural backgrounds may overwhelm them at large distances. Conversely, any artificial radio transmissions from other civilizations, if they exist, must cross similar gaps before they can be detected. The time delays involved mean that any exchange would unfold slowly, with years or decades between a message and its reply across distances of several light-years. This combination of physical separation and finite signal speed creates a natural quiet between stars. A silence does not necessarily imply the absence of other worlds or life, only that the scales involved impose long waiting times and faint signals. In this stellar neighborhood, the Sun is neither especially large nor small, neither very old nor very young. It is one main sequence star among many orbiting the center of the Milky Way, along with hundreds of billions of others. The nearby stars share this broad galactic motion, each on its own track, sometimes approaching one another over millions of years and then separating again. Their relative velocities are measured in tens of kilometers per second, which sounds swift in human terms, but is modest compared with the speed of light. Over a period of many millions of years, these motions lead to changes in the list of nearest neighbours. Stars that are distant today may approach the Sun in the far future, while present neighbours will drift away. The current arrangement is only a snapshot in a long dynamical history. Surveys that extend beyond the immediate vicinity show that stars populate a thin disk and a thicker halo around the galactic centre, with higher densities in some regions and lower densities in others. The local pattern is therefore part of a larger structure. Still, at this step of the journey, the focus remains on the scale set by a few light years to a few tens of light years. This scale is the first level at which individual planets become truly isolated in time and space, each bound to its star and each separated from other systems by gulfs that challenge both travel and communication. The contrast between the relatively compact solar system, even when extended to the Oort cloud, and the distances to the nearest stars marks a clear escalation in size. A star system, though large, is only a small unit in a broader network of similar systems arrayed along the disk of the galaxy. To grasp how big that network is, the narrative must draw back again, shifting from individual stars and their nearest neighbours to a view in which the Sun Alpha Centauri and all other nearby stars merge into a pattern of light that forms the spiral structure of the Milky Way itself. Within the wider neighbourhood of nearby stars, the influence of a single technological civilization introduces another subtle layer of scale. For most of the history of life on Earth, the planet is silent at radio frequencies, emitting only the weak natural signals of lightning auroras and thermal radiation. That changes in the late 19th and early 20th centuries, when radio transmitters begin to send powerful pulses and continuous waves into the atmosphere. These signals spread outward at the speed of light, forming an expanding bubble of artificial radio noise around the planet. At any given moment, this bubble marks the maximum distance at which a strong early transmission could in principle have reached. Its radius is set by the time elapsed since the first broadcast multiplied by the speed of light. After about 1 human century of radio activity, the bubble reaches a radius of roughly 100 light years. Inside that sphere, thousands of stars lie in every direction. The contents of the bubble include broadcasts intended for communication on Earth, such as early long-range radio, television, and radar. Much of this energy is directed sideways along the surface of the planet and scattered by the atmosphere, terrain, and oceans. Some fraction, however, escapes into space, especially from powerful radar systems and from transmissions beamed towards satellites and deep space probes. These signals fade with distance as they spread out over larger and larger spherical surfaces. At tens of light years, the strength of any single broadcast is greatly reduced, and detecting it against the background of natural cosmic radio sources would be challenging even with large antennas. Nevertheless, the concept of the radio bubble is useful as a way to picture the reach of human technology in space. It defines a region within which some trace of artificial signals has had time to arrive. Beyond that radius, even the earliest transmissions are still on the way. The shape of this region is not a perfect sphere with a sharp edge. Because transmissions start and stop vary in power and originate from many locations on Earth, at different times the pattern is complex. Gaps may exist in some directions and at some frequencies. Later, more focused signals sent toward specific spacecraft or toward candidate star systems form narrow beams that cut through the general wash of older broadcasts. These beams trace thin cones rather than shells, reaching far greater distances in those specific directions for the same transmitted power. The combination of all such emissions produces a patchy, irregular distribution of artificial radio noise. Despite this complexity, the simple picture of a roughly spherical bubble remains a helpful approximation for thinking about scale. Plotted on a map of nearby stars, this bubble encloses a diverse set of systems. Within a radius of 20 light-years, the Sun shares its region with several dozen known stars, mostly red dwarfs, and a few Sun-like stars. Extending to 50 light-years adds hundreds more. At 100 light-years, the number of enclosed stars rises into the thousands. Space missions such as Hipparcos and Gaia measure the positions and motions of many of these stars with high precision, building a three-dimensional map of the local stellar population. On this map, the Sun is one point among many, moving through the galactic disk on an orbit around the distant centre. The radio bubble appears as a sphere centred on the Sun filled with stars whose distances and trajectories are well measured. Some of these stars have known planets. Many of those planets are detected by observing tiny dips in starlight as they pass in front of their host stars, or by tracking small shifts in stellar motion due to gravitational tugs. The typical separations between planets and their stars are measured in astronomical units, but the separations between different planetary systems are measured in light-years. The map therefore mixes two scales: compact internal systems and large external gaps. The radio bubble overlays this structure with a temporal layer. Stars that lie close to the Sun might have received the first artificial signals decades ago. Stars at the current outer edge of the bubble receive them only now. Stars just beyond will receive them in decades to come, assuming that transmissions continue. For any hypothetical observers near those stars, the signals carry information about an earlier stage in the history of Earth, and its inhabitants frozen at the moment of emission. The finite speed of light ensures that each place in the galaxy has its own version of neighbouring histories offset in time. From Earth, the same effect applies in reverse. Light from nearby stars shows those stars as they were years or decades ago, not as they are in the present moment. The combination of distance and light speed separates now from observation, even at these relatively modest stellar scales. The radio bubble also underscores how small the reach of current technology is compared with the size of the galaxy. The Milky Way's disk spans about 100,000 light-years in diameter. A sphere with a radius of 100 light-years occupies only a tiny fraction of that volume. The great majority of stars in the galaxy lie far beyond the current radius of artificial signals from Earth. In most regions of the Milky Way, the existence of the Sun and its planets remains undetectable by any trace of human radio noise. Even within the bubble, detection is not guaranteed because the signals are faint and mixed with natural backgrounds. The smallness of this sphere relative to the galactic disk creates a strong contrast. On the scale of human movement, reaching orbit or the Moon is a major achievement. On the scale of planetary distances, sending probes to the outer planets takes decades. On the scale of interstellar distances, however, even light itself requires years to cross the separation between neighbours, and technological emissions have so far bathed only a small region in the immediate vicinity of the Sun. Beyond this region, the galaxy is effectively unaware of this brief burst of artificial activity. At the same time, the radio bubble offers a concrete, measurable structure that links human timescales to cosmic scales. Its radius grows by 1 light-year for each year that passes. If broadcasts persist for thousands of years, the bubble will grow accordingly, eventually encompassing a significant part of the galaxy. If transmissions cease, the edge of the bubble will remain fixed in time, and the region of space touched by artificial signals will form a finite shell that drifts along with the Sun and its neighbours around the galactic centre. Either way, the concept links the history of a single civilization to the geometry of a stellar neighbourhood. In the broader map of the Milky Way, this neighbourhood appears as a small patch of one spiral arm. To continue the journey of scale, the perspective must widen again, until the Sun, its radio bubble, and all its neighbouring stars merge into a single luminous pattern that traces the disk bulge and halo of the galaxy as a whole. When the view pulls back far enough that individual nearby stars begin to blur into a pattern, the Milky Way appears as a single system. It is a barred spiral galaxy, a wide disk of stars, gas and dust, with a central thickened region and a more diffuse halo around it. The disk spans about 100,000 light-years from side to side, while its thickness is much smaller, only a few thousand light-years from top to bottom in the main stellar layer. Within this flattened structure orbit hundreds of billions of stars along with clouds of gas that can form new stars and remnants of old stars that mark earlier generations. The Sun is one among these many stars. It sits in the outer half of the disk, not in the central bulge and not at the very edge, but in a minor spiral arm segment, often called the Orion Arm or Orion Spur. Its distance from the galactic centre is about 27,000 light-years. That means that even at the speed of light, a signal leaving the Sun would need tens of thousands of years to reach the core. In the opposite direction, an equal span of distance separates the Sun from the outer regions of the disk. The local neighbourhood of a few light-years that seems large on a stellar map now occupies only a tiny patch within one faint lane of the larger galaxy. The stars in the Milky Way do not stand still. Each one orbits the galactic centre under the pull of the combined mass of all the others, along with a large reservoir of unseen matter. The Sun moves on a roughly circular path around the centre at a speed of many hundreds of kilometres per second. At that speed, it still takes on the order of 200 million years to complete a single circuit. This duration is sometimes called a galactic year. Since the formation of the solar system about 4.5 billion years ago, the Sun has completed only a few dozen such orbits. During that time, spiral arms have shifted, star formation has occurred in different regions, and the arrangement of gas and dust has evolved. The present pattern of bright arms and dark lanes is therefore one frame in a long sequence of galactic history. From inside the disk, the Milky Way presents itself as a pale band of light across the night sky, more visible from dark locations than from brightly lit cities. That band is the collective glow of billions of distant stars whose individual light blends together. Dark patches within the band mark dense clouds of interstellar dust that absorb visible light. These clouds both hide and form stars. Within them, gas can cool and collapse under gravity, eventually igniting nuclear fusion in new stellar cores. Over time, massive stars form, shine brightly, and die in explosions that stir and enrich the surrounding medium, while less massive stars live longer and drift along the arms. Because dust blocks visible light toward the central regions, astronomers use wavelengths such as radio and infrared to map the structure of the entire disk. These observations reveal a central bar of stars that stretches across the inner galaxy, connecting to multiple spiral arms that wind outward. The Sun's orbit carries it through and between these arms, rather than keeping it fixed in a single bright lane. As it moves, it passes regions of higher and lower gas density star-forming areas and more quiescent zones. The galactic disk is not the only component. Surrounding it is a halo of old stars and globular clusters. Globular clusters are compact, roughly spherical groups containing hundreds of thousands of stars bound together by gravity. They orbit the galactic centre on paths that can tilt far above and below the plane of the disk. Their ages, often close to the age of the galaxy itself, provide clues about the early stages of galactic formation. In addition to these visible components, there is compelling evidence for a large amount of dark matter. This is a form of matter that does not emit, absorb or reflect light in any known way, but whose presence is inferred from its gravitational effects. When astronomers measure how fast stars and gas orbit at different distances from the centre, they find that the outer parts of the galaxy rotate faster than they would if only the visible matter were present. To explain this, they propose a halo of dark matter, extending well beyond the luminous disk, contributing most of the gravitational pull at large radii. The exact nature of dark matter remains unknown, but its inclusion in models allows the Milky Way to remain stable while rotating as observed. At the centre of the galaxy lies a dense region filled with stars, gas, and dust. Near the very core, precise measurements of the motions of individual stars reveal that they orbit an unseen mass concentrated in a very small volume. The best explanation for this object is a supermassive black hole known as Sagittarius, a star. Its mass is about 4 million times that of the Sun. Stars near it follow tight, fast orbits that loop around the central point in periods of only a few years or decades. Gas in the vicinity can heat to high temperatures and emit radiation at radio infrared and X-ray wavelengths. For most of the time, Sagittarius A star is relatively quiet compared with the more active centres of some other galaxies, but its presence defines the gravitational centre of the Milky Way. The disk bulge halo and dark matter all orbit around this central mass, while at the same time contributing to the overall gravitational field that shapes those orbits. The interstellar medium within the galaxy is a complex mixture of phases. There are cold molecular clouds where temperatures are low and density is relatively high, warm diffuse gas where atoms are partially ionized, and hot rarefied gas heated by supernova explosions. This medium fills the spaces between stars and participates in the cycle of starbirth and death. Supernovae and stellar winds inject energy and heavy elements into the gas, while gravity collects part of that gas back into new star-forming clouds. Over billions of years, this cycle slowly alters the chemical composition of the galaxy, enriching later generations of stars and planets with heavier elements forged in earlier stars. The Sun, with its complement of rocky and gaseous planets, belongs to a generation that forms after many such cycles benefiting from this enrichment. On the scale of the Milky Way, the human radio bubble described earlier shrinks to a nearly invisible point. A sphere with a radius of 100 light-years has a diameter of 200 light-years. Against the full diameter of the disk, that span is small, amounting to only a few tenths of 1% of the total. Most of the galaxy lies far outside any region touched by artificial signals from Earth. Even in terms of simple light travel time, the far side of the galaxy is so distant that a round trip for a beam of light would take on the order of 200,000 years. From the perspective of the galaxy, individual technological phases on a single planet may be brief, rising and falling on timescales much shorter than a galactic year. The Milky Way is not isolated. It coexists within a larger environment of nearby galaxies, some larger and some smaller, all moving under mutual gravitational influence and under the broader pull of the universe's expansion. Still, as a single gravitationally bound system, the galaxy itself represents a major jump in scale beyond any one star and its planets. It is a stellar city with many levels, a central district sprawling spiral lanes outlying clusters, and a vast invisible framework of dark matter. The Sun's place in that city is modest, a star in a quiet suburb of one arm. Understanding how large the galaxy is and how it is structured sets the stage for the next step outward, in which the Milky Way becomes only one member of a small group of galaxies bound together in a still larger configuration. When the Milky Way is seen as a single structure, the next step outward is to ask how many other galaxies share its immediate environment, and how they are arranged. The Sun's galaxy does not drift alone. It belongs to a small association called the Local Group, a collection of more than 50 known galaxies bound together by mutual gravity. The most prominent member besides the Milky Way is the Andromeda Galaxy, a large spiral system slightly more massive than the Milky Way, and located at a distance of about 2.5 million light-years. In visible light, Andromeda appears as a faint elongated patch in the northern sky, but detailed imaging reveals a disk's spiral arms, a central bulge, and a halo of stars and globular clusters. Another notable member is the Triangulum Galaxy, a smaller spiral lying a little farther away. Around these three main spirals orbit many dwarf galaxies, each with far fewer stars than the Milky Way or Andromeda. Some dwarfs are irregular in shape with scattered star-forming regions and distorted gas distributions. Others are more spheroidal with mostly old stars and little gas. The two Magellanic Clouds visible from southern latitudes as hazy patches near the Milky Way are examples of dwarf galaxies that interact strongly with their larger neighbour, showing tidal features and streams of stars and gas. The entire local group spans a region roughly 10 million light-years across. Within this volume, gravity between the galaxies is strong enough to hold them together against the general expansion of space. On these scales, the pull of nearby mass overcomes the tendency for distant objects to recede. Measurements of galaxy motion show that Andromeda and the Milky Way are on a collision course, moving toward each other at a speed of a few hundred kilometers per second. Their first close passage is expected to occur in several billion years. During that encounter, stars from both galaxies will move on new paths, gas will be compressed, and may trigger bursts of star formation, and the overall structure will change. Many simulations suggest that after several passes and mergers, the two spirals will settle into a more elliptical galaxy. For now, however, they remain distinct systems exchanging only faint tidal pulls across the gap. The smaller dwarf galaxies in the local group feel these pulls as well. Some orbit close to the Milky Way, their paths shaped by its dark matter halo. Others circle Andromeda more tightly. Tidal interactions strip stars and gas from some dwarfs, creating streams that trace their orbits. These streams serve as visible records of how the group has assembled over time, and how mass is distributed in the halos of the larger galaxies. The local group is not filled uniformly with galaxies. Most of the visible mass is concentrated in the two largest spirals and their immediate satellites. The space between these members is mostly empty, occupied by a thin gas with densities far below that of the gas within galaxies. This intergalactic medium carries traces of heavy elements, enriched by past outflows and supernova-driven winds, but overall it remains extremely diffuse. Radiation from galaxies and from the distant background keeps much of it ionized. At the same time, gravity from the combined mass of the local group tugs on this gas, guiding its slow motions over cosmic time. The group as a whole has a center of mass located somewhere between the Milky Way and Andromeda. Both galaxies orbit this common point while drawing closer together. Their satellite systems and associated dark matter halos overlap and interact even before the main disks meet. Beyond the visible galaxies, the local group also contains a large amount of dark matter. This unseen component provides much of the gravitational binding that keeps the group intact. Without it, the observed stellar and gaseous mass would not be enough to hold the galaxies together at their measured relative velocities. The dark matter halo of the local group extends beyond the luminous boundaries of its member galaxies, marking its overall gravitational territory within a wider environment. From the perspective of cosmic expansion, the local group occupies a special zone. On very large scales, galaxies recede from one another on average, with speeds approximately proportional to their separations. This relationship, known as the Hubble law, emerges from the expansion of space itself. However, on the smaller scales of groups and clusters, gravity can dominate and reverse this motion. Within the local group, the mutual attraction of its members cancels the general recession and produces local motions that reflect the specific mass distribution. Andromeda's approach is one clear example. It moves toward the Milky Way despite the overall expansion, because the fabric of space inside the group is held together by gravity more strongly than it is stretched by the expansion. This balance illustrates how the universe can be both expanding and locally bound at the same time. Observations of galaxies just outside the local group show a transition between these regimes. Distant dwarfs on the outskirts feel less binding, and more of the general expansion drifting away over time. More massive structures beyond exert their own tidal influence, tugging on the local group's center of mass and contributing to its overall motion through space. When their motions are corrected for the expansion, galaxies in the local group and its surroundings show a flow pattern that hints at larger gravitational structures nearby, drawing them in certain directions. Intergalactic space within the local group has its own structure, though it is subtle. There are filaments of slightly higher gas density relics of the pathways along which matter once flowed into the forming galaxies. There are also void-like regions where the density is even lower than average. These features reflect the early fluctuations in matter density that seeded the formation of galaxies and groups. Over billions of years, the local group emerges from these initial conditions as a bound system lying along one segment of a much longer filament that connects to other groups and clusters. The scale of the group also introduces a new sense of time. Light from Andromeda takes about 2.5 million years to reach Earth. The image of that galaxy in the night sky therefore shows it as it was when early human ancestors on Earth were just beginning to use tools. Any events in Andromeda that occurred since then have not yet been seen from here. Conversely, light from the Milky Way that reaches Andromeda now carries information about our galaxy, as it was 2.5 million years ago. On group scales, the separation between present and observed past becomes measured in millions of years rather than years or minutes. When the local group is drawn on a diagram, the Milky Way, Andromeda and Triangulum often appear as prominent nodes with dwarf galaxies clustered around them and with arrows indicating the directions of motion. Such diagrams compress three-dimensional reality into a plane, but they capture the main point. The group is small, compared with the scales of the larger cosmic web, yet large compared with any single galaxy. It is the first level at which galaxies themselves become the basic units, moving under gravity much as stars do within galaxies. The size of the local group expressed in millions of light-years already far exceeds the diameter of the Milky Way. Yet in the broader universe, groups like this are common, and often form subunits of even larger structures. Beyond the boundaries where the local group's dark matter halo thins and its gravitational influence fades, other groups collect into clusters. Among these, one dominant structure in the nearby universe, the Virgo cluster, begins to set the next scale. To understand how big the universe appears on those scales, the narrative must leave the local group and enter the wider region, where many such groups and clusters assemble into patterns stretching over tens of millions of light-years. Beyond the local group, the scale of structure increases again as many such groups collect into larger systems known as clusters. One of the nearest rich clusters to the Milky Way is the Virgo cluster, located in the direction of the constellation Virgo at a distance of roughly 50 to 60 million light-years. On the sky, this cluster spans a region larger than the apparent size of the full moon, but its galaxies are far too faint to see without telescopes. When those telescopes are turned toward the region, hundreds of galaxies come into view, scattered across a volume that spans several tens of millions of light-years. The Virgo cluster contains a mix of galaxy types. There are large spirals with star-forming arms, somewhat like the Milky Way and Andromeda, though often distorted by interactions. There are many elliptical galaxies which are more three-dimensional in shape and often dominated by older stars. There are lenticular galaxies which sit between spirals and ellipticals in form with disks but few obvious arms. There are also numerous dwarf galaxies with much lower luminosity. Near the centre of the cluster lies a giant elliptical galaxy, sometimes called a central dominant galaxy, that holds a large fraction of the cluster's starlight and resides in the deepest part of its gravitational potential well. The space between the galaxies in Virgo is filled with a hot diffuse gas called the intracluster medium. This gas is so thin that it does not emit much visible light, but its temperature, which rises to tens of millions of degrees, makes it shine in X-rays. Observations of this X-ray emission show that the intracluster medium contains more mass in gas than in all the stars of the cluster's galaxies combined. The gas is held in place by the cluster's gravity, which is itself dominated by a large reservoir of dark matter. When astronomers measure the speeds at which galaxies move within the cluster and combine that with the X-ray properties of the gas, they find that the total mass required to bind the system is far greater than can be accounted for by visible matter alone. Dark matter must provide most of the gravitational force. The galaxies in Virgo do not stand still. They move on orbits around the cluster's center of mass, influenced by the combined pull of all the mass in the system. Some move along elongated paths that carry them through dense central regions and then out toward the outskirts again. Others remain in more circular orbits. Collisions between galaxies are rare in the sense of physical stars striking stars because the separation between individual stars is so large, but gravitational interactions are common. When two galaxies pass close to one another, tidal forces can draw out long streams of stars and gas twist spiral arms, and even merge the systems. Over time, such interactions can transform spirals into ellipticals and redistribute gas within the cluster. In the dense central region where the number of galaxies per unit volume is highest, mergers are more frequent and the most massive ellipticals grow by absorbing smaller companions. The intracluster medium also records the history of the cluster's assembly. Gas that falls into the cluster's potential well is shock-heated to high temperatures. Supernova explosions and active galactic nuclei in member galaxies eject additional energy and heavy elements into the medium. As a result, the hot gas in Virgo is enriched with elements such as iron oxygen and silicon that were forged in stars and then dispersed. The abundance patterns in this gas provide clues to how many supernovae have occurred over the cluster's history, and how matter cycles between galaxies and their surroundings. The Virgo cluster does not exist in isolation. It sits within a larger region of overdense matter in the local universe. When the positions and redshifts of many galaxies in and around Virgo are plotted, a pattern emerges. The cluster sits near the junction of several elongated structures or filaments along which smaller groups and individual galaxies are aligned. These filaments extend outward for tens of millions of light-years, linking Virgo to other clusters and groups. Between them lie regions of relatively low galaxy density, sometimes called voids, where very few galaxies are found. The combination of clusters, filaments and voids forms a network sometimes referred to as the cosmic web. Virgo is one of the nearby nodes in this network. Redshift surveys, which measure how much the light from galaxies has been stretched by cosmic expansion, map this web in 3 dimensions. In such surveys, each galaxy appears as a point whose coordinates correspond to its position on the sky and its distance inferred from redshift. When many such points are plotted, the cosmic web structure emerges knots, where galaxy clusters reside threads, where filaments run, and large empty spaces where voids dominate. Virgo's role as a node in this web becomes clear in these maps. Gravity shapes this structure. In the early universe, small fluctuations in density grow over time as matter flows from underdense regions into overdense ones. Dark matter, which interacts primarily through gravity, collapses first into a network of halos and filaments. Ordinary matter made of atoms follows this pattern, cooling and forming stars within the densest regions. Clusters like Virgo arise where several filaments intersect and where the mass density becomes high enough to bind many galaxies together. This size of Virgo, measured in tens of millions of light-years, marks a jump in scale beyond the local group. Whereas the local group contains only a few dozen galaxies, Virgo contains thousands. The velocity dispersions of galaxies within the cluster, often reaching many hundreds of kilometers per second, reflect the depth of its potential well. Light travel times across the cluster span tens of millions of years. Light emitted from one side of the cluster takes that long to reach the other, and even longer to reach observers in more distant systems. As with the local group, the appearance of Virgo in the sky shows it at a time in the past. since its light has taken tens of millions of years to arrive the cluster, as observed now corresponds to an epoch when dinosaurs still walked the Earth. Any changes in its structure since then, such as mergers, new star formation, or the growth of its central galaxies, have not yet been seen from here. The Virgo cluster also influences the motion of the local group. The combined mass of Virgo and surrounding material exerts a gravitational pull on nearby groups and galaxies. When the observed velocities of galaxies in the local volume are corrected for the general expansion, a pattern of motion toward Virgo and related structures becomes visible. The Milky Way, Andromeda, and their satellites participate in this flow. Their paths through space are not straight lines, determined only by the initial expansion, but curved trajectories shaped by the attractors, represented by clusters and superclusters. This gravitational influence extends beyond Virgo itself. Mapping it requires tracking the peculiar motions of many galaxies, where peculiar motion refers to the deviation from the smooth expansion pattern. In doing so, astronomers begin to see that Virgo is part of an even larger arrangement of mass 1 that includes multiple clusters and superclusters, including the region known as Laniakea. That larger structure defines the next level of cosmic address after the local group and the Virgo cluster. At this stage of the journey, however, it is enough to note that clusters like Virgo show how galaxies are not evenly sprinkled through space. Instead, they gather into massive gravitationally bound systems that sit at the intersections of filaments in the cosmic web. The distances between such clusters are measured in tens of millions of light years, and their sizes are such that even a beam of light requires that same scale of time to cross from one side to the other. Compared with the already large size of a galaxy, the scale of a cluster moves the narrative into a regime where individual galaxies begin to resemble the stars in a still larger structure. To understand how big the universe appears on scales beyond this, the perspective shifts again from a single cluster like Virgo to the extended region of connected clusters and filaments that together define the supercluster to which the Milky Way ultimately belongs. On scales larger than individual clusters, the pattern of the cosmic web becomes clearer, and new structures appear that organize clusters and groups into still larger regions. The part of the universe that includes the Milky Way, the local group, and the Virgo cluster belongs to such a region called the Laniakea supercluster. The name, taken from a Hawaiian phrase meaning immense heaven, reflects the size of the structure that it describes. Laniakea is not a simple solid object like a galaxy or a cluster. Instead, it is a region of space spanning on the order of several 100 million light-years across, within which galaxies and clusters tend to flow toward a shared gravitational basin. The boundaries of this supercluster are defined not by sharp edges of matter, but by the directions of galaxy motions. In the expanding universe, galaxies in general recede from one another as space itself stretches. Superimposed on this smooth recession are additional motions caused by local gravitational pulls. These are called peculiar velocities. By measuring how galaxies in the nearby universe move after subtracting the part of their motion due to expansion, astronomers can trace the paths along which matter currently flows. When these flow lines are mapped, they reveal regions where streams of galaxies converge toward common centers. One such basin includes the Virgo cluster, the local group, and many other groups and clusters. Together, these make up Laniakea. Within this region, galaxies tend to move along filaments toward a gravitational center, located not at Virgo itself, but toward a nearby mass concentration often called the Great Attractor. This area lies in the direction of the constellations Centaurus and Norma, partly obscured in visible light by the dense stars and dust of the Milky Way's plane. Observations in radio-infrared and X-ray wavelengths help to pierce this zone of avoidance and reveal clusters of galaxies and hot gas that contribute to the mass of the attractor. In addition, an even more distant mass concentration known as the Shapley supercluster plays a role in shaping flows, but within the immediate cosmic neighborhood, the basin associated with Laniakea provides a useful way to define a supercluster. The size of Laniakea is large compared with structures described so far. Its characteristic diameter is on the order of 500 million light-years. Within this region, there may be on the order of 100,000 galaxies arranged along filaments and gathered into clusters and groups. The Virgo cluster is only one node within this network, and the local group occupies a modest position on one of its filaments. The distances between major clusters in Laniakea measure in the tens of millions of light-years, and the span from one side of the region to the other, in any direction, corresponds to a light travel time of hundreds of millions of years. Light that leaves a galaxy near one edge of the supercluster now will not reach the opposite edge for a time comparable to a significant fraction of the age of complex life on Earth. In such a setting, individual clusters play the role that galaxies play within a cluster, moving within a larger potential well and interacting through their combined gravity. The definition of Laniakea as a supercluster highlights another aspect of cosmic scale structures on these sizes are only marginally bound, if at all. Within a galaxy, gravity clearly dominates motions. Within a rich cluster like Virgo, gravity also holds galaxies together against the expansion, at least for long periods. On the larger scales associated with superclusters, however, the expansion of the universe competes more strongly with gravitational attraction. Parts of Laniakea may remain bound, while other parts may gradually separate as the expansion carries distant components beyond one another's effective reach. The supercluster is therefore better thought of as a kinematic region defined by current flows, rather than as a single object that will remain intact indefinitely. The idea of Laniakea helps to organize the notion of a cosmic address. One can describe the location of the solar system step by step. A planet in the habitable zone of a star, that star in the outer part of a spiral galaxy, that galaxy in a small group, that group within a nearby cluster, and that cluster within a supercluster whose flow lines converge toward a gravitational basin. Each step increases the scale by one or more orders of magnitude, yet each remains embedded in the next. On the map, traced by peculiar velocities, lines from our local group join those from many other systems and point toward the same broad region. In that sense, the local group participates in a larger motion, along with tens of thousands of other galaxies. The cosmic web around Laniakea does not end at its notional boundary. Filaments continue beyond connecting to other superclusters and clusters in adjacent regions. Outside the flow basin that defines Laniakea lie neighbouring domains where galaxies flow toward other attractors. One such region is associated with the Perseus-Pisces supercluster, another with the Shapley concentration. Together, these basins and their surroundings tile the nearby universe into a patchwork of flow regions, each containing many clusters and groups. The boundaries between them are somewhat like the divides between river catchments on a planetary surface, where water on one side eventually runs into one system and water on the other side into another. In the cosmic case, it is galaxies and dark matter that drift along the gravitational landscape rather than fluid, and the timescales are measured in hundreds of millions or billions of years. Although the comparison is limited, the underlying idea is that gravity shapes the large-scale distribution of matter into basins and ridges whose outlines can be traced by motion. Laniakea represents the basin that includes our own. The recognition of this structure illustrates how observational capabilities influence the perceived size of the universe. Before wide-angle redshift surveys and accurate distance measurements, the Milky Way and its immediate neighbours define the main known scale. The discovery of clusters like Virgo and the mapping of the cosmic web extend that view to tens of millions of light-years. Using galaxy flows to identify Laniakea extends it further to hundreds of millions of light-years. Each improved map reveals that the region once thought to be central or complete is in fact part of a much larger system. Yet even a volume hundreds of millions of light-years across is small compared with the scale of the observable universe as a whole. The radius of that observable region measured from Earth to the most distant galaxies presently detectable is on the order of tens of billions of light-years. Laniakea fills only a tiny fraction of that volume. On the largest maps, the entire supercluster appears as one of many similar structures, each a node in the web of matter that fills the observable cosmos. To understand how big the universe appears on those scales, the narrative now moves beyond this home basin to a view in which many superclusters, filaments, and voids together form the pattern of structure for much of the observable region, and where the limits of visibility and the expansion of space itself begin to define a cosmic horizon. On scales larger than any one supercluster, the pattern of matter in the universe reveals a network that spans much of the observable region. Individual galaxies, galaxy groups, and clusters become the small building blocks of an extended structure, often called the cosmic web. In this web, matter does not fill space uniformly. Instead, it collects along long thin filaments in flattened sheets, sometimes called walls, and in dense knots where filaments intersect. Between these features lie large voids regions where the density of galaxies is much lower than average. Surveys that measure the positions and distances of hundreds of thousands of galaxies show this pattern clearly when plotted in 3 dimensions. In such maps, the nearby universe resembles a scattering of points arranged along arcs and threads, with large, roughly bubble-shaped empty regions separating them. Structures like the Sloan Great Wall and other extended filaments stretch across hundreds of millions of light-years, tying together many clusters and superclusters into larger complexes. These structures are not solid in the everyday sense because the galaxies within them remain widely separated by intergalactic space. Instead, the walls and filaments mark where matter has been slightly more abundant than average throughout cosmic history, allowing gravity to slow the local expansion and gather material along preferred paths. The voids, by contrast, are regions that began slightly less dense and have become emptier as matter flowed out toward the surrounding filaments. The cosmic web seen at the present epoch has grown from very small initial seeds. Observations of the cosmic microwave background radiation, the afterglow of the hot early universe, show tiny variations in temperature and density across the sky. These variations are at the level of tens of parts per million, but over billions of years they grow under gravity. Regions that start slightly denser attract more matter and become the nodes and filaments of the web. Regions that start slightly less dense lose matter to their surroundings and become voids. Dark matter, which interacts primarily through gravity, provides most of the mass that collapses into this network. Ordinary matter follows cooling and forming stars in the densest places. In this way, the pattern of galaxies and clusters seen today preserves a record of the initial conditions imprinted in the early universe. The size scales involved range from tens of millions of light-years for individual filaments and voids to hundreds of millions of light-years for extended walls and supercluster complexes. When a slice through the universe on these scales is drawn, each galaxy is represented as a single point. The points cluster along curves and planes, leaving large empty regions between. The local group, the Virgo cluster and the Laniakea supercluster, all appear as parts of one such arrangement, occupying one node and strand among many. The cosmic web continues in all directions out to the limits of current surveys. Beyond those limits, it likely extends in similar fashion, though details there remain unmeasured. As the scale increases, an important transition appears. On small and intermediate scales, matter is clearly clumped into galaxies, groups, clusters, and filaments. On the larger scales within the observable region, however, the distribution becomes statistically uniform. This means that when one averages over very large volumes, each region contains roughly the same amount of matter as any other, even though the detailed arrangement of filaments and voids differs from place to place. This transition from strong clustering to large-scale uniformity is one of the key observations that support the idea that the universe is homogeneous and isotropic on the larger scales. Homogeneous means that the average properties are the same in all locations when measured over large enough regions. Isotropic means that on average the universe looks the same in all directions. These assumptions underpin many cosmological models. The cosmic web therefore has two faces. On one hand it shows rich, intricate structure on the scales of tens and hundreds of millions of light years with named features and distinct regions. On the other hand, when one steps back far enough to encompass a large fraction of the observable volume, these features blend into a pattern that can be described by simple statistical measures. In that statistical sense, no particular supercluster filament or void is special. The region around the Milky Way appears to be typical of many others when viewed on those scales. Mapping the cosmic web is an ongoing process. Large redshift surveys cover only parts of the sky, and some directions are obscured in visible light by the plane of the Milky Way. Future surveys in many wavelengths and with new instruments aim to fill in these gaps, extend the maps to greater distances, and measure the motions of galaxies more precisely. In addition, studies of weak gravitational lensing, where the paths of light from distant galaxies are slightly distorted by intervening mass, provide another way to trace the distribution of dark matter that underlies the web. These measurements refine knowledge of how structure has grown over cosmic time and how it may continue to evolve. They also test models of cosmic expansion and the properties of dark energy, the component that appears to drive the accelerated expansion of the universe on the larger scales. As these maps improve, they sharpen the contrast between the finite volume currently observable and the much larger, possibly infinite universe beyond. The cosmic web inside the observable region can be measured and described. Beyond that region, however, the structure can only be inferred from theory, and from the assumption that the laws of physics and the statistical properties of matter remain the same. This boundary between what is mapped and what is unknown marks another step in understanding how big the universe appears. Inside the horizon set by light travel time and expansion, the web of galaxies is partly charted and quantified. Outside that horizon, any continuation of the pattern, any new structures or any departures from uniformity remain beyond direct observation. The next step in the journey therefore turns to the idea of the observable universe itself, the radius out to which light has had time to reach us since the beginning of cosmic expansion, and to the question of how that observable sphere relates to the larger, perhaps much larger universe that may lie beyond it. On the larger scales that can be directly observed, the universe presents itself as a finite window in space and time. This window is called the observable universe. It is centered on the point where Earth happens to be now, but its definition does not depend on any special status for this location. It depends only on how far light and other signals have been able to travel since the hot early phase from which the universe expands. The age of the universe, according to current measurements, is about 13 and a bit billion years. If space was static and unchanging, one might expect the radius of the observable region to be simply the distance that light could travel in that time. In reality, space itself has stretched while the light has been in flight. As a result, the most distant regions that can now be seen are much farther away than a simple product of age and light speed would suggest. When measured in the coordinate system used by cosmologists to track expanding distances, the radius of the observable universe is about 46 billion light years. This means that the sphere of space from which light has had time to reach Earth since the beginning of the expansion has a diameter of about 92 billion light years. Beyond that sphere there may be more of the same web of galaxies, clusters and voids, but light from those regions has not yet arrived. The image of the observable universe is layered in time. Light from relatively nearby galaxies at distances of tens or hundreds of millions of light-years shows them as they were when multicellular life had already developed on Earth. Light from more distant galaxies at billions of light-years shows them as they were when the universe was younger and star formation rates were higher. At the greatest distances where individual galaxies can still be detected, their light left them when the universe was only a small fraction of its current age. Beyond these, there is a more uniform glow that fills the sky at microwave wavelengths. This is the cosmic microwave background radiation, a faint remnant of the time when the universe was hot and dense enough that matter and light were tightly coupled. As the universe expanded and cooled, it reached a point about 380,000 years after the beginning of expansion, when electrons and protons combined to form neutral atoms. At that time, the fog of charged particles that had trapped light became transparent. Photons last scattered from matter during that transition, and have been travelling through space largely unhindered ever since. Today those photons are observed as the microwave background, with a characteristic temperature of just under 3 degrees above absolute zero. The surface in space from which this background light was last emitted forms a sphere around the observer. In maps of the observable universe, this sphere is sometimes called the surface of last scattering. It marks a practical limit to how far back in time electromagnetic observations can see, because before that era the universe is opaque to ordinary light. The cosmic microwave background therefore acts as a kind of wall, in the sense of direct observation, though information about earlier times can still be inferred through other means such as patterns in the background itself and relic particles. The expansion of the universe is described in simple terms by a scale factor that grows with time. Galaxies are not flying through space in all directions from a single centre. Rather, the distances between most unbound galaxies increase as space itself stretches. On large enough scales, this stretching follows the Hubble law, in which the recession speed between two distant galaxies is approximately proportional to their separation. The constant of proportionality called the Hubble constant sets the current rate of expansion. For nearby galaxies outside the local group, this relationship explains observed redshifts where spectral lines are shifted toward longer wavelengths. For very distant galaxies, the expansion has been acting for a longer time and the redshifts become large. Their light is stretched so much that features originally emitted in visible or ultraviolet bands now appear in the infrared or even in longer wavelengths by the time they are detected. At great distances, the recession speeds implied by the Hubble law can exceed the speed of light, not because galaxies themselves move through space faster than light, but because the space between them grows. The speed limit set by relativity applies to motion through space, not to the expansion of space itself. As a result, there are regions of the universe that are and always will be receding from any given point faster than light. Light emitted from such regions now will never reach the observer. This situation introduces several distinct horizons. One is the particle horizon, which marks the boundary of the observable universe and corresponds to the furthest distance from which light has had time to arrive since the beginning of expansion. Another is the event horizon, which marks the boundary beyond which events can never affect the observer in the future, even if one waits indefinitely. In a universe where expansion is accelerating due to a component called dark energy, the event horizon lies at a finite distance. Some galaxies that can be seen today lie beyond this event horizon. Their light emitted billions of years ago has managed to reach us, but any light they emit in the future will never arrive because the expansion carries them away too quickly. Over vast timescales, these distant galaxies will fade from view as their light is shifted to longer wavelengths and diluted. The observable universe will then contain fewer visible structures, even though the underlying universe may continue as before. The presence of these horizons shows that the observable universe is not the same as the entire universe. It is simply the part that has been in causal contact with a chosen observation point up to now. Other regions may exist beyond the particle horizon, sharing the same physical laws and similar structures, but they are permanently separated in terms of direct signals. In many cosmological models, the universe is much larger than the observable part, possibly infinite in extent. In such cases, the observable universe is like a limited patch cut from a larger continuous fabric. Even in models where the universe is finite, its total size may be many times larger than the observable radius. The exact global shape and size remain uncertain, because observations can probe only so far. Measurements of the cosmic microwave background and of the distribution of distant galaxies suggest that space is very nearly flat on large scales, which is consistent with both large finite and infinite scenarios. No clear signatures of a small closed universe, such as repeated patterns in the sky caused by light wrapping around, have been seen. Thus, while the radius of the observable universe can be stated with some confidence, the overall size of the universe beyond that radius remains an open question. In terms of scale, this means that the values given for the observable region, tens of billions of light-years in radius, are lower limits on how big the universe might be. There could be many more superclusters, filaments and voids beyond the horizon, arranged in patterns similar to those mapped nearby, or there could be variations on even larger scales that current observations cannot reveal. The structure within the observable universe suggests that matter and energy follow the same physical rules everywhere that can be tested. Whether this uniformity extends without limit beyond the horizon, or whether new behavior appears at scales that are currently hidden, is part of the mystery that remains when one asks how big the universe really is. At the edge of the observable universe, the story of scale reaches a boundary set not by a physical wall, but by time and expansion. Beyond the surface from which the cosmic microwave background is last emitted, space almost certainly continues. The best models of cosmic evolution suggest that the same physical laws apply beyond the observable horizon, and that the matter and radiation there follow similar patterns of clustering and expansion. Yet no direct signal from those regions has had time to arrive. The question of how large the universe really is therefore separates into two parts. One part concerns the size of the observable region, which can be measured and described. The other concerns the extent of the universe beyond that region, which must be inferred from theory and from the limited clues available within the observable volume. A key ingredient in these models is the idea of cosmic inflation. According to this concept, in a very early phase, the universe undergoes a brief period during which the scale factor grows extremely rapidly, driven by a form of energy with unusual properties. This rapid stretching smooths out any initial curvature and irregularities over enormous regions, making the observable universe appear nearly flat and homogeneous today. Quantum fluctuations in this early stage become stretched to cosmic scales, and later seed the small density variations that grow into the cosmic web. Inflation, if correct, implies that the region that inflates is much larger than the part now visible. In many versions of the theory, inflation does not end everywhere at once. Some regions stop inflating and form universes like the one observed, while inflation continues elsewhere. This leads to the idea of a much larger, perhaps infinite space, in which many observable regions like ours exist, each with its own cosmic horizon. Some speculative models even allow for variations in physical parameters between regions, creating a multiverse of domains with different detailed properties. At present, however, evidence for such extensions remains indirect. Observations of the cosmic microwave background and of large-scale structure are consistent with inflation having occurred, but they do not uniquely fix how far it extends, or whether it continues beyond the observable patch. Another way to approach the question of size is to consider the geometry of space. Measurements of the microwave background and of distant galaxies suggest that on average, space is very nearly flat when averaged across large scales. A perfectly flat universe can be infinite, or it can be finite but extremely large if it has a more complex global topology. If the universe is slightly positively curved, it might be finite with a total volume that could eventually be calculated from precise curvature measurements. If it is slightly negatively curved, it would be open and infinite. Current data place strong limits on any deviation from flatness, indicating that if the universe is finite, its size must be many times larger than the observable region. No clear patterns indicating a small closed geometry, such as repeated images of the same structures seen in different directions, have been found. This pushes any boundary if it exists far beyond the current horizon. The presence of dark energy, which appears to drive an accelerating expansion, adds another layer to the question. As time passes, more and more distant galaxies cross beyond the event horizon and become permanently unobservable. Even if the universe is spatially infinite, the portion that can ever be in contact with any given point remains finite. Over extremely long times, observers bound to a single gravitationally bound structure, such as a future remnant of the local group, may see only their own system and a fading background. The cosmic web beyond their bound region will have thinned from view not because it has vanished, but because expansion has carried it outside the range from which signals can be received. In that far future, the observable universe from that location will be smaller in content, even if the global universe remains large or infinite. Cosmic variance presents another limit. Only one observable universe is available to study. Structures on scales comparable to the observable radius occur only a few times within that volume, so statistical estimates of properties on those scales carry inherent uncertainty. This means that even perfect measurements within the observable region cannot fully reveal what lies beyond or determine definitively whether the larger universe shares exactly the same properties everywhere. Some questions may therefore remain open, not because instruments are insufficiently sensitive, but because the information simply does not exist within the available data. Taken together, these considerations outline a range rather than a precise answer. The universe is at least as large as the observable region, with a radius of tens of billions of light-years today. It is likely much larger, perhaps so much larger, that the observable patch is only a small part of the whole. It may even be infinite in spatial extent. Inflation, large-scale flatness, and the observed uniformity of the cosmic microwave background all support this view, but none of them yet compel a single final conclusion. The true size of the universe remains beyond current measurement, hidden beyond horizons that expand only slowly as time passes. Each new survey and each new map reveals more detail within the observable sphere tracing structures ever closer to its edge. Yet the boundary itself remains a limit imposed by the combined effects of light travel time and cosmic expansion. When the question of how big the universe really is asked, the most accurate answer at present stays incomplete. The observable universe has a well-defined size that grows as time goes on, but the full universe beyond that visible shell may extend without bound, or it may curve back on itself at scales that are still far beyond reach. Between these possibilities, present observations do not yet choose. The result is a cosmos that is quantified in part and open in part, with known structures nested inside deeper unknowns, and with the ultimate extent of space and matter still an unanswered question.